All right, so today on campus we did some enrichment problems on the gas laws. And so here are the problems that we did today. You can also download this file from the course website. Or if you're just watching this online, you can pause the recording, try it for yourself, and then resume when you're ready to see the answers. So here are problems 1 through 5. Pause it, try it for yourself, and then hit resume when you're ready. And then here are 6 through 10. So we're going to go through these now here on campus so that everybody's got the answers and everybody's questions are addressed. So let's look at each one of these, all dealing with the gas laws. All right, you enter a wing eating contest. You don't win, sad face. But you play second. It's pretty good, right? I'd be not able to place fifth because I don't have much room left. But anyway, you play second and you win a balloon. Yay. And you get a balloon filled with helium. If the volume of the balloon is 2.5 liters inside the restaurant, where the temperature is 24 degrees Celsius, what will happen to the volume of the balloon when you get in your car? And we're going to assume that it's summer, so the temperature in your car is 42 degrees Celsius. Now, before we do these problems, I actually want to pull up, or does anyone have that handout handy that I gave you? Let's just put this up here. This is what you'll be given on the exam on your reference page. All right, I will be giving you the gas laws, so you don't have to memorize them. So let's just have that handy so we can pick the appropriate gas law. All right, so what we need to do is we're going to list our variables. So you get volume. Volume is 2.5 liters. And the temperature is 24 degrees Celsius. So that's V1 and T1. You take your balloon out to your car, let it come to thermal equilibrium with your car. And the temperature in your car is 42 degrees Celsius. And so we want to know what's the new volume in the balloon. All right, so do we keep volume in liters? Is that an okay unit? Yes. What about temperature? Do we keep it in Celsius? What do we do to make it Kelvin? Right, we add 273, right? Plus 273. So that gives me 297 Kelvin and 315 Kelvin. So now we've got volume and temperatures, right? So now we just pick the right gas law. So V1 over T1 equals V2 over T2, right? That's the gas law we're using. V1 over T1 equals V2 over T2. So 2.5 over 297 is equal to V2 over 315. So most students, I don't know if that's what you do, you guys just cross multiply? Is that what you prefer to do? No, that's what most students typically tend to do. So I get V2 is equal to, I'm keeping 2 sig figs, 2.7 liters. Did you get that? Rounded to 2 sig figs. Does that make sense that the volume would go up if you go to your hot car where the temperature goes up? Yeah, right? Why? Temperature goes up, which means more collisions. Right? The volume's going to expand. Any questions on number 1? Everybody good on how we do number 1? All right. So if you just list out your variables and then pick the correct gas law, that's really all there is to this. Just make sure you make any necessary conversions. All right, give myself some room here. You're inflating a balloon. You take a deep breath and then exhale 1.8 moles of air into the balloon, making the volume in the balloon become 683 milliliters. But oh no, before you can tie the balloon, some of the gas escapes and the volume decreases by 100 milliliters. How many moles of gas escaped from the balloon? Right? This happens to me all the time when my kids ask me to blow up balloons. I can't tie it fast enough. So let's look at what we've got here. We've got a volume, and we've got number of moles, and then the volume decreases by 100. So that's volume, right? So let's list out our variable. Initial volume is 683 mils. And initial number of moles is 1.8. And then how do I get V2? How would I get V2 here? You just subtract it, right? Volume decreases by 100. So 683 minus 100, so that's 583 milliliters. And we want to know how many moles escaped. Now, we're going to have to figure out what the new number of moles is and then subtract that from what we originally had. Does this make sense? We're going to have to do some subtraction. All right, so which gas law deals with volumes and moles? V1 over N1 equals V2 over N2. Oh, but before we do anything here, can we keep our volume in mils? What would that be in liters? 0.683, right? And 0.583. All right, so V1 over N1 equals V2 over N2. So we're going to find out number of moles, and then we're going to subtract that from what we originally had. So try not to stand right in front of the camera, 0.683 over 1.8 is equal to 0.583 over N2. So if you just cross multiply, I got N2 to be, we're going to round it to 2 sig figs, right? Yep, 1.5. So now we want to know how many moles escaped. Right, so number moles escaped when I didn't tie the balloon fast enough would just be N1 minus N2. So 1.8 minus 1.5, so 0.3 moles. And that's what escaped. Does that make sense, how we did that one? Because the problem is how many moles escaped. That's the key word. Okay. You find the new number of moles and then subtract it from what you initially had, and that tells you how many got away. Does that make sense? The key to that one's reading the problem. All right. Get a new marker while I'm at it. Say low. All right, let's look at number 3. You are tired and take a big yawn. If we assume that a deep breath has a volume of 500 milliliters, so let's start listing our variables. Volume, oops, 500 mils. And that room temperature is 25 degrees Celsius. Atmospheric pressure is 760 millimeters mercury. And that 20.9% of the air that we breathe is oxygen. How many grams of oxygen gas are inhaled in a big tired yawn? Okay, so when we take a deep breath, that's what we're referring to, right? We're breathing in air Breathe in a 500 milliliter volume that's at 25 degrees Celsius and 760 millimeters mercury pressure, and we want to know how many grams of O2 am I inhaling when I do that. So, is there a gas law that deals with volume, temperature, pressure, and grams? There's not, is there? Which is the only one that makes sense to use here? PV equals nRT, right? Because if I can get N, then I can convert that into grams, right? But before we do anything, we need to do some unit conversions, right? Because can I leave volume in milliliters? No, what does it need to be? Liters. So, oops. That would be 0.500, and there is a decimal there. Liters. How do I convert that to Kelvin? Add 273. So that's 298 Kelvin. What about pressure? 760 millimeters mercury. That's 1 atmosphere, right? Because 760 millimeters mercury, the conversion factor is 760 for 1 atmosphere, right? So that's 1.0 ATM. Okay, so now we can plug into PV equals nRT. All right, so 1.0, 0.500 is equal to N. What's R? R is a constant, right? We don't have to solve for it. 0.08206, and the units are liter atmosphere per mole Kelvin. And then the temperature is 298. So I got 0.0204 moles. Did you? Does anyone need me to show that arithmetic? I'll do it just to be safe. I'll do it just to be safe because I'm seeing some mixed reviews here. So I say 1 times 0.5, 0.500 is equal to 0.08206 times 298. 24.454 N divided by 24.454 divided by 24.454 0.5 divided by 24.454 gives me 0.0204. If you didn't get that answer initially, do you see where you made your mistake? Now, the problem says only 20.9% of that is actually oxygen gas. So, if I want number of grams of O2, this is total number of moles, right? This right here is the total number of moles in this sample of all the mixture, right? This is a mixture. So how do I get just the oxygen? If I've got a pie chart, right, and only, that looks about 20.9 is O2, this whole thing might be 0.0204. How do I get what this piece of the pie is? Multiply by 20.9%, right? Do you see why we're multiplying by 20.9? Because this is a mixture that I'm breathing. When I take a breath, I'm taking a mixture. Right? I'm breathing mostly nitrogen. Only 20.9, what I'm breathing is actually oxygen gas. So to get the percent oxygen, number of moles O2, since it's 20.9%, would be 20.9% times 0.0204. Right? So that would be 0.209 times 0.0204. So times 0.209. So this is 0.00427 moles of O2. Does everyone see why we multiply by 20.9? Because I'm breathing in a mixture. That's the total number of moles of the nitrogen and the CO2 and everything else in the room, right? I only am interested in the mass of oxygen I'm breathing. That's why I multiply by 20.9%. But the problem didn't ask how many moles of O2, it asked how many grams of O2. So what would I do next? I got one more step I need to do. All right, so O2, each oxygen is 16, right? So 16 and 16 is 32. So there are 32 grams per mole. So that gives me times 32. 0.1367. I can only retain how many sig figs? 2. So that's 0.14 grams. Do we agree? Do we agree on this one? You made a mistake, you see we made it. Questions on this one? Right? These problems are designed to make you think a little bit. I want you to use the gas law and then think a little bit about it. Right? We multiply by 20% because I'm only interested in the O2. That's why we multiply by 20%. All right, let's look at number 4. Give some space here to write. Okay. The tire is filled with 35 liters of gas in the winter, when the average temperature is 20 degrees Fahrenheit, which is negative 6.7 degrees Celsius. So we've got a volume is 35.0 liters, and the temperature is negative 6.7 degrees Celsius. So that's B1 and T1. By spring, assuming you don't, drive over any nails and all that good stuff, the average temperature in your neck of the woods is 18.3 degrees Celsius. What's the new volume in the tire? Okay, can we leave volume in liters? Yep. What about temperature? Can we leave it in Celsius? We want to convert to Kelvin, so we add 273, right? So I got for T1, 266.3 Kelvin, and for T2, I got 291.3 Kelvin. V and T, which gas law gives us that relationship? V1 over T1 equals V2 over T2, right? So V1 over T1 equals V2 over T2. So let's plug in our variables. 3.5. 35.0 over 266.3 is equal to V2 over 291.3. If we cross multiply, I get V2 to be 38.2 liters. Does that answer make sense? If the temperature goes up, should the volume increase as well? Yes, it should. Questions on number 4? Feel good about number 4? All right. let's do number 5. Number 5, a balloon contains 3.5 moles, so that's N. It occupies 85 liters, that's a big balloon. 85 liters at a pressure of 780 torr. What is the temperature inside the balloon in degrees Celsius? Okay, can we leave N as 3.5 moles? No conversions needed there, right? Volume, can we leave that in liters? Can we leave a pressure in torr? No, what do we need to do? What's the conversion factor? Well, what unit do we need to convert to first? We're converting to what unit? ATM, right? 1 atmosphere is equal to how many torr? That's on your conversion sheet. That's 760, right? So 780 torr times 760 torr per 1 atmosphere. So let's see. That's 1.03 ATM. So which gas law is the only one that makes sense to use here? PV equals nRT, right? So let's use PV equals nRT, solve for T. Now, T is going to come out in what unit? When I use PV equals nRT, it's going to spit out T with the unit of what? The default answer is going to be Kelvin, right? I'll have to then convert it to degrees Celsius. So PV nRT. So 1.03 times 85 is equal to N. Oops, N is not what we're solving for, T is what we're solving for. 3.50826 T. All right, so let's see here. I got T equals 305 Kelvin. Do you need me to do the arithmetic or do we agree on that number? Now, how come T's in Kelvin? How do I know T's in Kelvin? Just look at the units of R if you forget, right? R has the units liter atmosphere per mole Kelvin, right? The units of R need to be able to cancel out all the other units. So K is my unit. So that's 305 Kelvin. How do I get that converted back to degrees Celsius? Right, we're going to subtract 273 to get Celsius. So I got 31.8 degrees Celsius. Do we agree? Because you're technically subtracting 273.15. That's where the decimal comes from. If you rounded, I'm not going to be upset. But you're technically 0.15. That's where the decimal's coming from. Do we agree? Yes? Okay. Let's look at number 6. Page break. All right. Solid calcium carbonate decomposes at 1200 degrees Celsius to form carbon dioxide gas and solid calcium oxide. If 2.5 liters of CO2 are collected at 1200 degrees Celsius, what will the volume of this gas be when it cools to room temperature, 25 degrees Celsius? So do we need to write a balanced equation here? You can, but is it necessary? Is this a stoichiometry problem? No, all right? You're collecting a gas, and it's at a temperature of 1200 degrees Celsius. That's really hot, right? So T is 1200 degrees Celsius, and its volume is 2.5 liters. Cursor's like right in the way. Here we go. So that's my initial temperature and volume. What will the volume of this gas be when you cool it to room temperature? So T2 is 25 degrees Celsius, and we want to know what's the new volume. All right, what's this temperature in Kelvin? How do we get that? We add 273.15 technically, right? I got 1473, and then this is 298 Kelvin. Done a lot with this same gas law. I should have been more creative. Should have picked different gas laws to work with here. V1 over T1 equals V2 over T2. So 2.5 over 1473 is equal to V2 over 25. Cross multiply. I got V2 equals 0.51 liter, 2 sig figs, right? Yes. That's a pretty significant drop in volume. Does that make sense that the volume would go down so much? Why would the volume, yeah, that does make sense. Why? Why is that reasonable? If you lower the temperature drastically, what are you going to do to the volume? You're going to reduce it drastically, right? You're going to reduce the volume. Do we agree on number 6?
Yeah, I want to say 25, 32.
Oh, but yeah, I was just plugging in the wrong number. Yeah. Thank you. Yes, I just plugged it in wrong. Any other questions on 6? All right. Let's look at number 7. Going to a wedding. It's about that time of year, right? Wedding season. Although by the time you're in your 30s, most of your friends are already married. It's all baby showers now. All right. You go to a wedding and the bride and groom decide to be unenvironmentally friendly. Instead of throwing birdseed or blowing bubbles, they all release helium balloons. If your 4.5 liter balloon, so volume is 4.5 liters, is filled to a pressure 1.01 atmospheres, what will the new volume be when it reaches the upper atmosphere where the pressure is 0.600 atm? So this is pressure and volume question. So we list out our variables. Which gas law makes sense? P1 V1 equals P2 V2, right? So P1 V1 equals P2 V2. So we don't need to make any conversions here because liters and atmospheres are fine. 4.50, 1.01 is equal to 0.600 V2. So I got V2 equals 7.58 liters. Do we agree? Why would the volume expand? This gas is, I mean, this volume is expanding. The pressure's gone down, right? There's less atmospheric pressure up there. All right. Let's look at rate. A 75-liter drum holds 62 moles of gas. That's a lot of gas. At 215 degrees Celsius, what's the pressure inside the drum? So volume is 75 liters. Number of moles is 62 moles. Temperature is 215 degrees Celsius, and we want to know pressure. There's only one gas law that works here. What is it? PV equals nRT, right? Volume's fine in liters. N is fine in moles. Temperature, what do we need to do here? Add 273.15 technically. So I got 488 Kelvin. R is a constant, right? And that'll be on your reference page. Right? So we're solving for P. So PV equals nRT. So P times the volume is 75 is equal to 62.08206 times temperature 488. I got P equals 33 atmospheres. Is that high pressure or low pressure? What's the pressure in this room approximately? We're really darn close to sea level. So our pressure is pretty close to 1. So is 33 atmospheres high pressure or low pressure? That's high pressure, right? That's 33 times what we're experiencing right now. We wouldn't want to be in this room if the pressure was 33 atmospheres. But you got 62 moles of gas. You would expect that many moles. That's a lot of collisions. That would be a very high pressure. So that is reasonable, given the fact that it's 62 moles. Two more to go. Number 9. You are doing a gas compression experiment using a 500 milliliter syringe. So that's a volume. Right? Volume is 500, there's a decimal, milliliters, at an initial pressure of 0.96 atm. You press the plunger down to a volume of 35.5 milliliters. What's the new pressure in this syringe? Can we keep volume in milliliters? What do we need to do? Convert to liters, right? Now this has 3 sig figs, so make sure when we convert to liters, we maintain those 3 sig figs, 0.500 liters, right? That's got 3 sig figs. Keep those 3 sig figs, okay? And then when we convert milliliters to liters here, that would be 0.0355 liters. Gas law, look at our list. P1V1 equals P2V2. So P1V1 equals P2V2. 0.96 times 0.500 is equal to P2 times 0.0355. So P2, I got to be 14 atmospheres. We can only keep 2 sig figs because of that one. Would you expect the pressure to go way up? You've taken this much gas and you've smooshed it down to this much gas, right? That's a lot more, and that's a lot less space. So yes, you would expect the pressure to go way up, and it does. Questions on 9? Okay, last problem. A certain gas canister can tolerate internal pressures up to 210 atmospheres. So that's its limit. Beyond that, it cannot tolerate it anymore. So a 2-liter canister, so that's the volume, and it holds 140 grams. Well, there's no gas law that involves grams. So what am I going to have to do with this grams? Convert it to moles, right? So 140 grams, and this is argon. Argon's molar mass is 39.99. So I got 3.501 moles, right? 4 sig figs, 4 sig figs. So N is 3.501 moles. Is heated to 1,350 degrees Celsius. We can't leave temperatures in Celsius, so what do? We add 273. So I got 1,623 Kelvin. And so, will the canister explode? So what do I need to solve for in order to decide if the canister is going to pop? Solve for pressure, right? And the only gas law that would allow me to do that is PV equals nRT. So P is what I'm solving for. V is 2.0. N is 3.501. R is a constant, 0.08206 liter atmosphere per mole Kelvin. And my temperature is 1,623. So I got a pressure of 233 atmospheres. So does this can explode? Yes, it does. All right, how do we feel on the gas laws? Feeling pretty good? All right, that's where we are going to stop for today.